The examples in this video go with lesson 7.1, polar coordinates. Example 1. Plot the points whose polar coordinates are given. Part A, positive 3, positive 5 pi over 4. All right, starting at the center, or at the pole, we're going to find the line, or the ray, that extends out toward 5 pi over 4. That's going to be this one right here. And then the 3 tells me how many circles I need to move forward. So let's see, here's 1, here's 2, here's 3. This point right here is positive 3 and positive 5 pi over 4. And I'm just going to put letter A right here to represent that was for part A. Part B, positive 4 and negative 7 pi over 6. All right, remember our angles move counterclockwise when they're positive, and they move clockwise when they're negative. So while positive 7 pi over 6 is located right here, negative 7 pi over 6 will rotate back this way. This is negative 6 pi over 6, and then we go one more to negative 7 pi over 6. So we'll be following the line that goes toward 5 pi over 6. And then the 4 tells me how many circles I need to move toward 5 pi over 6. We have 1, 2, 3, 4. And there's the point, positive 4, negative 7 pi over 6. And there are other names that go with it as well, which we'll talk about in another example. Part C, positive 2.5, 4 pi. Let's see. This is 2 pi. If we keep rotating around, this will take me to 3 pi. And if I keep going around, this will bring me back to 4 pi. And so we're going to follow the arrow or the ray that goes towards 0. And I'm going to move forward 2.5 circles. So that should put me right here in between positive 2 and positive 3. And this is point C. And then for the last one, negative 3 and 4 pi over 3. Again, we're going to be starting right here at the pole. The ray that moves toward 4 pi over 3 is right here. But since my radius is negative 3, instead of moving toward 4 pi over 3, I'm going to move backwards away from 4 pi over 3. But I'm going to stay on this same line. Okay, so we're actually going to back up, and we're going to move toward positive pi over 3. And I'm going to go 3 circles there. So we have 1, 2, 3. This point is negative 3, positive 4 pi over 3. And this is point D. Example 2. Given positive 7, positive 3 pi over 2 in polar coordinates, find 2 other polar coordinate representations. Now the graph is over here for our convenience, but we don't really have to use it, but I'm going to go ahead and graph it anyway. Both of my coordinates here are positives, so I am going to start here at the pole, and I'm going to move forward toward 3 pi over 2. That's going to be this ray down here. And then we're going to go out 7 circles. 1, 2, 3, 4, 5, 6, 7 will put me right here. All right. We want to find 2 other polar coordinate representations for positive 7, positive 3 pi over 2. Okay. Well, one option I have is I can move, or I can rotate up to pi over 2, and then I can move backwards 7, and I can do that because 90 degrees and 3 pi over 2 fall on the same straight 180 degree line. So another option I have is negative 7 and positive pi over 2. All right. Another way that I can do this is I can rotate negative negative pi over 2, and then move forward 7. So we could have positive 7 and negative pi over 2. And then it didn't ask me for the third one because each of these points we should be able to represent 4 ways. And let me just go ahead and give you a hint. This one has been named with a positive positive. This one's been named with a negative and a positive. This one's been named with a positive and a negative. So the pair that we're missing is our negative negatives. All right, and our options are we can rotate negative 3 pi over 2, which means we'll be heading this way, but we can go backwards 7. Negative 7, negative 3 pi over 2. All right, so negative 3 pi over 2 would bring me around to here, but instead of moving forward with a positive radius, I'm going to move backwards with a negative radius, and that's going to put me at this point right down here. Example 3, convert the ordered pairs in the polar coordinates to rectangular coordinates. Part A, positive 5, positive pi. We're going to use our conversion factors that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And remember, my polar coordinates are given to me, r is first and theta is next. So if I want to convert this into its rectangular coordinates, x and y, x will be equal to r times the cosine of theta, and y will be equal to r times the sine of theta. Well, let's see. The cosine of theta is negative 1, so that means x is going to be equal to 5 times negative 1. The sine of pi is equal to 0. That means that y is going to be equal to 5 times 0. And that means the rectangular coordinates will be negative 5 and 0. Part B, negative 10 and negative 2 pi over 3. Again, I'm going to use my conversion factors up here that x is equal to r times the cosine of theta and y is equal to r times the sine of theta. X will be equal to negative 10 times the cosine of negative 2 pi over 3, and y will be equal to negative 10 times the sine of negative 2 pi over 3. That means x will be equal to negative 10. Let's see, the cosine at negative 2 pi over 3, that's going to be down in quadrant 3, and the cosine is going to be negative 1/2 there. So we'll have negative 10 times negative 1/2. Y will be equal to negative 10 times the sine of negative 2 pi over 3. Now remember, negative 2 pi over 3 is down in quadrant 3, and the sine down in quadrant 3 is going to be negative, so this is going to be negative square root of 3 over 2. Negative 10 times negative 1/2, that's positive 5. And then negative 10 times negative square root of 3 over 2, that's going to be positive 5 times the square root of 3. Example 4, convert negative 2, negative 2 square root of 3 from rectangular coordinates to polar coordinates. Give 2 representations, one of them with r greater than 0 and one of them with r less than 0. So you want to have one positive radius and one negative radius. All right, and I am going to use the fact that x is equal to r times the cosine of theta, and that y is equal to r times the sine of theta. And that means that theta is either going to be equal to the inverse cosine of x divided by r, or theta could be equal to the inverse sine of y divided by r. That's how I'll get my theta coordinate when I put it in the polar. And then to get r, I'm going to use the fact that x squared plus y squared is equal to r squared. That's my Pythagorean theorem, and it's also the formula we use for any points on the unit circle. Okay, all right, let's find r first. So this will be my x coordinate, this is going to be my y coordinate. X squared plus y squared is going to be equal to r squared. This is going to be 4. This is going to be 12. And 4 plus 12 is going to give me 16. And then if we square root both sides, you know that radical and that power will cancel. So it looks like my radius is going to be 4. But remember, I have to use the positive radius here and the negative radius here. Okay, let's figure out what theta is going to be equal to. Now, this point, because it's in rectangular coordinates, we know is located in quadrant 3. Okay, and in quadrant 3 on the unit circle, we know those points are between pi and 3 pi over 2. So my theta is going to need to be in between pi and 3 pi over 2. And I guess I'm just going to use the top one here. It doesn't really matter which one we use. We're going to have to convert it back over into quadrant 3 anyway. All right, so theta is going to be the inverse cosine of my x value was -2, that was right over here, divided by r that we just found down here, which is 4. That means we're looking for the inverse cosine of -1/2. In other words, we're looking for the angle where the cosine is -1/2, and I want the one in quadrant 3 where the angle is -1/2. So that's going to be 4 pi over 3. So one way I can represent this point, -2, -2 squared root of 3 in polar coordinates is I can have +4 and then +4 pi over 3. Now if we look at a picture of that, let's see, my pi over 4 is going to be here, my pi over 6 is going to be here, so my pi over 3 is going to be here. My point is located right here. Now, if I can think of another way to get here other than rotating to 4 pi over 3 and then moving forward 4 times, well, remember there are 4 different ways to represent this point. And if I back up 4 pi over 3, remember this line right here is +pi over 3. So one thing I could do is I could rotate to +pi over 3 and then move backwards 4 circles. In other words, we could have -4 with +pi over 3. And now I've satisfied the conditions of my problem because it said to give me a point, one with a positive radius and one with a negative radius. So we are in fact finished. But I'm going to go ahead and figure out what the other two are, even though it didn't ask me. All right, another option that I have right here when I started the poll, we can rotate to, rotate backwards. Hang on a second. All right, so our other options are going to be, let's see, we've got our positive, we have our negative, positive. All right, let's see if we can find another one here. If we rotate our angle in the negative direction, so to get from here around to here, we're going to have to do -2 pi over 3. that's going to bring me to this ray right here. Then we'll just move forward 4 circles. Right. This gives me my positive, negative. So all I'm missing is my negative, negative. So if I start here and I rotate 5 pi over 3, that's negative 5 pi over 3. And then that's going to bring me to this ray right here. But remember, my point's back here, so I'm actually going to move away from pi over 3 toward this one right here. So that's going to be a negative 4. And that gives me my negative, negative right there. So there are my 4 answers, but this had only asked me for 2 of them. Example 5. Convert positive 2, negative 3 from rectangular coordinates to polar coordinates. Give 2 representations, one with a positive radius and one with a negative radius. So this problem is going to be very similar to the previous one. The only difference is what we're going to find is the answer that we get is not going to be something that's located on our unit circle. It's not going to be one of our nice angles. And so we're actually going to have to use the calculator to help us figure out what our angle is going to be, what theta is going to be. But I'm still going to be using my formulas. So my angle could be the inverse cosine of x divided by r, or it could be the inverse sine of y divided by r, or actually we could use the inverse tangent of y divided by x. And I didn't use it the last time, but I could have. But the tangent, as you know, is not located there on the unit circle, and so it was easier to figure it out either with the cosine or the sine because those coordinates are located on my circle. But just keep in mind I did have that option to use on the previous problem. And I probably will be using this one on this particular problem because I already have the foreknowledge that this is not going to be one of my special angles on the unit circle. So I'm going to have to use the inverse tangent key on my calculator to get to the angle that I want. All right, we're still going to use, though, the x squared plus y squared is equal to r squared. So let's find r first. We have x squared plus y squared equal to r squared. That gives me 4 plus 9. And 4 plus 9 is actually 13. And then when we square root both sides, we know that the radical and the power are actually going to cancel. That means r is going to be equal to the square root of 13. Now, we do want a positive one and we do want a negative one. So I'll need a point with positive root 13 and one with negative root 13 as my radius. And we'll figure that one out in just a minute. Okay, let's find the angle. The angle is going to be the inverse tangent of y divided by x. Now, this is exact. Because if I put it into the calculator, I'm going to actually have to round this thing. So we'll do both. We'll do the exact and we'll do the approximate. If I actually do theta is equal to the inverse tangent of negative 3 over 2, and I'll do that in my calculator, then we can figure out what our angle is, and we'll just round it out to 1 decimal place. Actually, let's round it up to 3 decimal places here. All right. So according to my calculator, theta is equal to negative 0.983. All right. This is in quadrant 4. But let's go ahead and get the positive coterminal angle that goes with this. In other words, let's add 2 pi to this. And that's going to give me 5.300. And this will be our approximate answer. All right, so one option that I have is the pair of positive square root 13 and then 5.300. That's the approximate. The exact one would be positive square root 13 inverse tangent negative 3/2. And this is not going to work for me because this point right here is in quadrant 2 and these points right here are in quadrant 4. So I'm actually not going to be able to use this after all. All right, let's take away this part right here. There we go, just that part. This part came out of the calculator right here, okay? All right, so here's what's going on. We've got our angle down here in quadrant 4, negative 0.983. What we need is to have our angle up here in quadrant 2 because that's where my rectangular coordinates are located. All right, so if this angle is 0.983, that means this angle right here is also 0.983. And so how I get this angle on this side over here is if I rotate all the way around here, that's pi, that's too far. So I need to back off 0.983. So instead of adding 2 pi here, I'm going to add pi. And what that's going to do is that's going to put my angle in quadrant 2 instead of in quadrant 1. So let's add pi to that. That gives me 2.159. That means that instead of having these ordered pairs here, we will have positive square root 13 and then the inverse tangent of negative 3/2 plus pi. Remember, we had to add that pi to get up in quadrant 2. This is our exact. Our other option is we can have positive square root of 13, positive 2.159. This is our approximate. And notice in both cases here, I have a positive positive. And now I need to get one where the radius is actually a negative. All right, let's take a look at the picture as we have it right now. The square root of 13 is in between positive 3 and positive 4. And my angle, remember, is over here in quadrant 2. So that means my point is somewhere right here in between the 3rd and the 4th circles. Okay. Now I want to be sure and move backwards away from an angle so that I can wind up back here in quadrant 2. I want to move backwards because I want my radius to be negative. That means I need to know this angle down here. Well, that's pretty convenient because we already found that angle. It's right here. We said that one was in quadrant 4. So that means if we move or we rotate to negative 0.983, then we can rotate backwards negative square root of 13 circles, and that will give me this point right here. Okay, and again, we're moving down 0.983, negative 0.983, and instead of moving forward, we're going to have to back up negative square root of 13. And that's my coordinates. And this is actually my negative negative, and this is also an approximate. Now, how do I get to the exact? Well, here we go. We've already found the exact right here. Just remember, we're moving backwards away from that square root of 13. And then the inverse tangent of negative 3/2. Honestly, y'all, I think doing the approximate solutions is going to be okay, but I think that any problems that you do in the book and possibly the ones that you do in ALEKS are going to ask you for the exact answers, and so I wanted to show you both of them. But when you turn stuff in for me and when you do it on the test, I think that approximate answers are going to be okay. Example 6, write an equivalent equation using polar coordinates. Part A, y is equal to -3. I am going to use my conversion factors, and that is x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now, when we're converting these into their polar form, we usually solve for r. So once we've done our substitution, whatever equation we have left, we're going to need to solve for r, unless there is no r, and then in that case we will be solving for theta. Okay. In part A, I have a y over here, so I am literally going to substitute that y with what I know y is equal to, which is r times the sine of theta. This means this equation becomes r times the sine of theta is equal to -3. Now remember what I said, once I've gotten rid of my x's and y's, what I want to do is solve for r. That means we're going to have to divide away this sign on both sides. And we have r is equal to -3 divided by the sine of theta. And we can actually simplify that a little bit more because I know that -3 divided by the sine of theta is the same thing as -3 times 1 over the sine of theta. And the reason I did that is because I know that 1 over the sine of theta is the same thing as the cosecant of theta. So we can actually simplify this into r is equal to -3 times the cosecant of theta. And that is the equation that I want right there. For part B, we have y is equal to x squared. Once again, I know what y is equal to, and I'm going to use that same substitution. So we're going to have r times the sine of theta over here. Now, as far as the x is concerned, I also know what x is equal to. I can substitute this one right here in there, but I don't want to forget to square everything. So we're going to have r times the cosine of theta, and then all of this is squared. So this is my y, this is x squared. Right, let's simplify this a little bit. We have r times the sine of theta equal to r squared times the cosine squared of theta. And again, remember we want to be solving this for r. So let's first of all divide this r over here. That will cancel those out. And we have the sine of theta equal to r squared. I'm sorry, just plain old r, not r squared. Take that out, because that's going to cancel with one of those. And then we have a cosine squared of theta. We're solving for r, so let's divide the cosine squared to the other side. We have r is equal to the sine of theta over the cosine squared of theta. We can actually simplify that a little bit further because I know that the sine over the cosine squared of theta is the same thing as the sine of theta over the cosine of theta times 1 over the cosine of theta. So what I did was I just broke this apart into two fractions that I can multiply and get this as my answer. And the reason I did that is because the sine over the cosine will simplify into the tangent, and 1 over the cosine actually simplifies into the secant. And so here is the equation that I want. Example 7, write an equivalent equation using rectangular coordinates and identify the type of curve the equation represents. All right, for part A, we have r equal to -3. Now, the things that I have to work with, I know that r squared is equal to x squared plus y squared, and I know that theta is equal to the inverse tangent of y divided by x. I also know that theta is equal to the inverse sine of y divided by r, and that theta is equal to the inverse cosine of x divided by r. So I can use any of these. Now the whole idea is the equation that I have now has r's and thetas in it, and I want to use these conversions to eliminate all my thetas and r's. I want to turn everything into x's and y's, because that's what I can graph on my regular graph paper. Now one option that I have when we start here at part A is I am actually allowed to raise both sides to the second power. Now the reason I'm going to do that is because I have an r to the first power, and there's nothing up here that has just a plain old r in it. And so if I do that, that's going to give me an r squared equal to 9. The good thing about this is I actually have a substitution I can make for r squared. It's right here. So I can turn this into x squared plus y squared equals 9. I'm finished here, y'all, because the r's and thetas are gone. This is my equation for part A, x squared plus y squared equals 9. Now, as far as identifying the curve, these equations you probably don't know. They're part of the conic sections, and we're going to do the conic sections in chapter 10. But if you do recognize this, it does in fact draw a circle on the graph paper when you try and graph it out. All right, part B, we have theta equal to -pi/4. All right, so I'm going to take out my theta and I'm going to replace it with my tangent equation here, or my inverse tangent. So we know the inverse tangent of y divided by x is going to be equal to -pi/4. Well, if this side is the inverse tangent, that must mean that y over x is actually equal to the regular tangent of -pi/4, and conveniently, -pi/4 is on my unit circle. Now remember, tangent is y divided by x. -pi/4 is located down here in quadrant 4, where the coordinates are +√2/2 and -√2/2. And when I take the tangent, y divided by x, this is actually going to turn into -1. The tangent at -pi/4 is -1. All right. And then I can turn this into a proportion and cross multiply, and we will have y equal to -x. And that is my equation for part B. All the thetas are gone. Everything's turned into x's and y's. Part C, r is equal to 6 times the secant of theta. All right, let's go to the other slide so we have a little bit of room. All right, one thing I notice is that there's no sines and cosines in this problem. All right, so let's fix this so that we have sines and cosines in there, because if I do, then I'm going to be able to do something with this. All right, I know the secant is the same thing as 1 over the cosine, and I'm just going to change this just slightly because I went a little bit too far. This is going to be 1 over the cosine of theta times the secant, which turns it into 6 over the cosine of theta. Okay. All right, and now I actually have my cosine theta in here. What I'm going to do here is I'm going to treat this like a proportion, and I'm going to cross multiply. So over here on the left, we're going to have r times the cosine of theta. And on the right, we're going to have 1 times 6, which is just 6. Now remember my conversions. I know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Well, look at there. There's r cosine theta. There's an r cosine theta. I can make my substitution. This whole side is just equal to x. And there we go. There's my rectangular equation. X is equal to 6. This is actually a vertical line. And it is a vertical line where x is equal to 6. And I forgot to identify this one over here. Y is equal to negative x. This is also a line when we draw it on the graph paper. Okay, part D, we have r equal to 6 times the sine of theta. And again, I'm going to go over to the next slide so we have a little bit more room. Here we have r equal to 6 times the sine of theta. Now notice, I have the sine of theta. I need an r in there so that I can substitute a y, and there's not one. So one option that I have is I can actually multiply both sides by r. That's going to give me r squared equal to 6 times r times the sine of theta. This part right here, we have a substitution for. That's just a y. So we know r squared is equal to 6y. Now I'm partially done because I have a y in here. Now I just need to eliminate the r squared. Well, remember, r squared is just equal to x squared plus y squared. And so we can substitute x squared plus y squared on this side, like so. Okay, so now we've gotten this far, and we haven't really worked with completing the square since 171, and there is a better way to do this so that we can figure out exactly what type of a picture this will draw on the graph paper. And we will use a process called completing the square, and again, we will be doing this more in chapter 10 when we study the conic sections. So for right now, for our intents and purposes, this part is going to be good enough. But I'm going to go ahead and show you how to complete the square on this so that we know exactly what the picture is going to be drawing, and we'll know which one of the conic sections this is. All right, and I'm going to do that by subtracting the 6y from both sides. All right, this is going to leave me with x squared plus y squared minus 6y. This is going to be equal to 0. All right, now what I'm going to do is I'm going to group my y's together like this. And I'm going to do this process called completing the square. And I only need to do it on the y's, and that's because I just have the x squared here by itself. There's no linear term for the x's. But what I'm going to do is I'm going to add something right here, and I want to be sure and add that same something back here. And whatever I'm adding here is going to be my middle term, negative 6. I'm going to divide it by 2, and then what answer I get, I'm going to square that, and that is what we're going to replace in here and in here. So it's the negative 6. I'm taking half of it and then squaring it. So half of negative 6 is negative 3. Negative 3 raised to the second power is positive 9. And so I'm going to add 9 in here, and I'm going to add 9 in here. All right, what has this done for me? Because now I just have this great big polynomial equation. X squared plus y squared minus 6y plus 9 equals 9. Well, it turns out this polynomial right here will actually factor. And if you factor it, you'll find out it factors into y minus 3 times y minus 3, or a better way to write that would be y minus 3 squared. And it looks like this is going to be another circle. And the center of the circle is going to be at 0 and 3.